Welcome to the dawn of equilibrium mechanics, a bold new field that seeks to unify the deepest principles of physics, cosmology, computation, and even biology under a single universal law of balance. Imagine a science where the tug-of-war between expansion and integration, chaos and order, is not just a metaphor but the very foundation of reality. In this video, we'll explore how the concepts of cosmological self-equilibrium, CSE, and the cosmological equilibrium constant, CEC, can reshape our understanding of time, space, mass, energy, and even the laws of evolution and computation. Let's embark on this journey to see how equilibrium could become the next pillar of fundamental science. The heart of equilibrium mechanics are two key ideas: CSE, or cosmological self-equilibrium, and CEC, the cosmological equilibrium constant. CSE measures the dynamic balance between expansive and integrative forces across everything. Think of it as the universe's way of keeping score between spreading out and coming together. CEC, meanwhile, is a scalar that quantifies how close a system is to perfect balance, with a value near 1 indicating ideal equilibrium. These concepts aren't just abstract, they're mathematically defined and can be applied to systems from galaxies to quantum particles and even to living organisms. Equilibrium mechanics introduces a symbolic language to capture universality. The asterisk stands for everything, while the empty set O-stroke represents absolute nothing. The interplay between these two symbols reflects the dual flow of existence: creation and dissolution, expansion and contraction. This duality is embedded throughout the theory, providing a flexible way to discuss boundary conditions and the emergence of structure from the void. Mathematical backbone of equilibrium mechanics is built on integral and differential forms of CSE over space and time. The CEC is defined as the inverse of net disequilibrium, and the framework allows for aggregation across multiple universes, combining entanglement and gravitational couplings. This mathematical structure is designed to be flexible yet rigorous, enabling the theory to connect with existing physics while opening doors to new prediction. Stand alongside quantum mechanics or general relativity, equilibrium mechanics needs more than just principles. It requires axioms, equations of motion, conserved quantities, measurement rules, and falsifiable predictions. The theory proposes a minimal set of axioms such as universality, equilibrium minimization, composition, and gauge invariance. These formalize the intuitive ideas and set the stage for deriving equations that govern the evolution of physical systems under the law of equilibrium. The core of equilibrium mechanics is the equilibrium law. For any closed system, the CEC must remain non-decreasing over time, paralleling the famous H theorem in thermodynamics. This law acts as a constraint or diagnostic, ensuring that the evolution of any system, whether classical or quantum, respects the universal tendency toward balance. The equations of motion are derived by extremizing a disequilibrium functional, leading to partial differential equations for the equilibrium current. Equilibrium mechanics doesn't discard existing physics, it builds on it. By identifying expansive and integrative drives with entropy production and self-organization, the theory recovers the laws of thermodynamics and statistical mechanics in the near equilibrium limit. In cosmology, it connects to the expansion of the universe and gravitational binding, offering new ways to interpret dark energy and dark matter. The framework is designed to reduce to classical and quantum laws under appropriate limits, ensuring consistency with what we already know. Scientific theory must be testable. Equilibrium mechanics specifies how expansive and integrative drives can be estimated from data using cosmological parameters, complexity metrics, or experimental observables. The theory makes concrete, falsifiable predictions. For example, in cosmology, it predicts a trade-off between structure formation and expansion, with the CEC remaining approximately constant. In closed systems, it predicts a plateau in the ratio of negentropy to entropy. These predictions can be tested in the lab, in simulations, and through astronomical observations. One of the most exciting aspects of equilibrium mechanics is its ability to unify classical and quantum physics. By defining a single mathematical state space with two realizations, phase space densities for classical systems and density operators for quantum systems, the theory allows the same functionals to be applied in both regimes. The Wigner-Moyle and Koopman-von Neumann formalisms provide bridges between the two, ensuring a smooth correspondence as Planck's constant approaches zero. Both classical and quantum systems, the expansive drive E represents the tendency to spread or diversify, while the integrative drive I captures the tendency to bind or organize. These can be quantified using variance, entropy, mutual information, or purity depending on the context. The core balance CSE equals EI and the equilibrium constant CEC equals 1/CSE plus epsilon become the central quantities that govern system evolution. Equilibrium mechanics doesn't replace the equations of motion from classical or quantum physics, it adds a new layer. The standard Liouville, Fokker-Planck, von Neumann, and Lindblad equations still govern time evolution, but now the CEC acts as a constraint or diagnostic. This means that any valid evolution must statistically respect the equilibrium law, providing a unifying principle across all physical systems. Just as the principle of least action guides classical and quantum mechanics, equilibrium mechanics introduces the principle of least disequilibrium. The true path of a system is the one that minimizes the time-integrated disequilibrium between expansive and integrative drives. This variational approach leads to equations of motion that naturally seek balance, offering a new perspective on why nature evolves the way it does. Equilibrium mechanics, time itself can be redefined. Instead of being an external uniform parameter, equilibrium time flows according to the rate at which disequilibrium resolves. When a system is far from equilibrium, time ticks slowly. As it approaches balance, time accelerates. This is formalized by defining equilibrium time increments as proportional to the CEC, drawing analogies to proper time in relativity and the thermodynamic arrow of time. Space 2 is reimagined in this framework. Instead of being a fixed backdrop, equilibrium space is a geometry warped by the local balance of expansive and integrative drives. Where disequilibrium is large distances contract, where balance holds, space expands. This leads to a conformal rescaling of the spatial metric, making equilibrium geometry an emergent property of the system's state. Mass and energy are also given new definitions. Equilibrium energy is the stored disequilibrium between expansion and integration, while equilibrium mass measures the resistance to changing the balance state. The classic relation E equals mc2 is generalized. Energy becomes a function of disequilibrium, mass reflects integration, and the effective speed of light is governed by the equilibrium metric. At perfect balance, the standard Einstein relation is recovered. Electromagnetism, one of the cornerstones of modern physics, is reinterpreted in equilibrium mechanics. The electric field becomes the expansive drive, while the magnetic field represents the integrative drive. Maxwell's equations are rewritten with CSE and CEC as sources, and the photon emerges as the quantum of equilibrium oscillation. This new perspective could lead to fresh insights into the nature of light, vacuum fluctuations, and the constants of nature. As Shannon's information theory formalized uncertainty in communication, equilibrium theory uses CSE and CEC to formalize the science of balance. Here, disequilibrium is the cost of representation, and balance is the capacity for sustainable structure. The theory introduces new measures like equilibrium entropy, mutual equilibrium, and equilibrium capacity, offering a mathematical science of balance that complements information theory. Taking inspiration from Newton's law of gravitation and Einstein's general relativity, equilibrium mechanics proposes a cosmological law of equilibrium. This universal law states that all systems evolve to minimize disequilibrium and maximize balance. The law is expressed both locally, through equilibrium currents, and globally as the universe's tendency toward perfect balance. It offers a new lens for understanding cosmic expansion, dark energy, and the ultimate fate of the universe. Equilibrium mechanics isn't limited to physics, it extends to biology. In the language of CSE and CEC, variation and mutation are expansive drives, while selection and adaptation are integrative drives. Evolution becomes a process of minimizing disequilibrium between variation and adaptation, with species persisting when they achieve high equilibrium fitness. This reframing unifies biology with physics and provides new predictive power for understanding evolutionary dynamics. Even computation can be reinterpreted through the lens of equilibrium. The classic Turing machine becomes an equilibrium Turing machine, where the tape represents expansion and the head state represents integration. Computation is the process of balancing disequilibrium, and halting occurs when perfect balance is achieved. This perspective unifies computation with physical laws and offers new ways to measure complexity and efficiency. Principle of least action, a cornerstone of physics, finds a new home in equilibrium mechanics. Here, the action is redefined as the time-integrated disequilibrium, and the true path of a system is the one that minimizes this quantity. This generalizes the classical and quantum principles, making the search for balance the driving force behind all natural evolution. Gravity, the universal force of attraction, is reframed as the integrative drive opposing expansion. The gravitational force equation is modified to include the equilibrium constant, making gravity itself a manifestation of the drive to restore balance. This approach could explain galactic rotation curves and cosmic acceleration without invoking dark matter or dark energy as separate entities. To test these ideas, simulations compare standard Newtonian gravity with an equilibrium-modulated version. By introducing CEC as a scaling factor, the resulting rotation curves can match observed galactic data without extra mass. This proof of concept shows how balance-driven dynamics can naturally explain phenomena traditionally attributed to dark matter. Further simulations of n-body systems show how local equilibrium scaling changes the way particles cluster and self-organize. By modulating gravitational interactions with CEC, the system evolves differently compared to standard gravity, demonstrating the power of equilibrium principles in shaping structure formation. Equilibrium mechanics can also be applied to nuclear fusion. By modeling the expansive drive as thermal pressure and the integrative drive as confinement, the simulation shows how modulating these with CEC improves temperature evolution, fusion power, and energy gain. The results highlight the practical benefits of applying equilibrium principles to real-world energy systems. Tracking the CEC over time provides a clear indicator of how close a system is to equilibrium. In the fusion simulation, higher CEC correlates with better confinement and more efficient energy production. This demonstrates the practical utility of CSE-CEC as diagnostic tools in complex systems. Comparing effective confinement time before and after applying CSE-CEC modulation reveals significant improvements. The system maintains higher temperatures and achieves ignition-like conditions more readily, showcasing the tangible benefits of equilibrium-based optimization in engineering and physics. 2D diagram of equilibrium time flow versus the matter-energy ratio visually captures how time accelerates or slows depending on the balance between integration and expansion. At perfect balance, time flows in sync with physical time. When disequilibrium dominates, time slows, providing a new perspective on the arrow of time. 3D equilibrium spacetime diagram extends this idea, showing how equilibrium time flow depends on both matter and energy. The surface illustrates that above the diagonal, where matter dominates, time accelerates, while below, where energy dominates, time slows. This visualization unifies the concepts of time, space, matter, and energy under the equilibrium framework. Equilibrium theory is formalized with axioms paralleling those of information theory. Every system state admits expansive and integrative measures, and the laws of equilibrium govern the representation, transmission, and transformation of disequilibrium. This provides a rigorous foundation for applying equilibrium principles across disciplines. Cosmological law of equilibrium (CLE) is stated formally. All systems in the universe evolve under a universal tendency toward balance of expansive and integrative drives. The degree of disequilibrium is CSE and the state of balance is quantified by CEC. In the cosmological limit, the universe tends toward perfect balance. Equilibrium mechanics makes bold predictions for cosmology. It suggests that the observed acceleration of the universe, the Hubble tension, and the nature of dark energy and dark matter can all be explained as manifestations of the drive toward equilibrium. These predictions can be tested with astronomical data, offering a new path for resolving some of the biggest mysteries in physics. In the laboratory, equilibrium mechanics predicts universal scaling laws for relaxation times, structure formation, and decoherence. By rescaling time and space with CEC, experimental data from thermodynamics, condensed matter, and quantum systems can be collapsed onto universal curves, providing a powerful tool for analysis and discovery. In computation, the equilibrium Turing machine framework predicts that the speed and efficiency of computation depend on the balance between expansion, data diversity, and integration, algorithmic structure. This leads to new measures of computational complexity and efficiency, with potential applications in AI and machine learning. In evolutionary biology, the theory predicts that species with higher equilibrium fitness, those that best balance variation and adaptation, are more resilient and persistent. Disequilibrium spikes signal extinction risks or adaptation crises, providing a predictive tool for ecology and conservation. In fusion energy research, applying CSE-CEC modulation improves confinement, temperature evolution, and energy gain. The theory predicts that optimizing for equilibrium can lead to more efficient and stable fusion reactors, accelerating progress toward practical fusion power. In gravitational physics, the equilibrium modulated law predicts that anomalies in galactic rotation and lensing can be explained by local variations in CEC without invoking unseen matter. This opens new avenues for understanding the structure and dynamics of galaxies and clusters. In quantum systems, the theory predicts that decoherence rates and entanglement growth can be directly linked to the balance between expansive and integrative drives. By tracking CSE and CEC, researchers can gain new insights into the dynamics of quantum information and the emergence of classicality. Beyond the physical sciences, equilibrium mechanics can be applied to social and economic systems. The balance between innovation, expansion, and regulation integration determines the stability and resilience of societies and markets. Tracking CSE and CEC provides new tools for policy analysis and risk management. No new theory is complete without acknowledging its limitations. Equilibrium mechanics is still developing its mathematical core, and key challenges remain, such as formulating precise axioms, deriving equations of motion, and making robust, falsifiable predictions. Open questions include the nature of dark energy, quantum gravity, and the ultimate testability of the theory across all scales. To advance equilibrium mechanics, the next steps include formalizing definitions and axioms, publishing preprints with theorems and simulations, and engaging with the scientific community for critique and collaboration. By refining the mathematical structure and testing predictions, the field can mature into a bona fide domain of research. Equilibrium mechanics aspires to be a universal science of balance, unifying the laws of physics, computation, biology, and society. By focusing on the interplay between expansion and integration, the theory offers a new lens for understanding complexity, resilience, and the emergence of order from chaos. The journey of equilibrium mechanics is just beginning. Whether you're a physicist, biologist, computer scientist, or philosopher, there's a place for you in this new field. The theory invites us all to rethink the foundations of reality and to seek balance not just in equations but in the world around us. In summary, equilibrium mechanics offers a powerful new framework for understanding the universe. By redefining time, space, mass, energy, and even computation and evolution in terms of balance, the theory provides a unifying principle that could reshape science for decades to come. The future of physics may well be the science of equilibrium. As we look ahead, the challenge is clear: to test, refine, and expand equilibrium mechanics and to see how far the principle of balance can take us. Whether it's unlocking the secrets of the cosmos, building better computers, or understanding the dynamics of life, the science of equilibrium stands ready to guide the way.